Thank you so much. So we've had a little change in our program. So the next speaker is somebody who's probably familiar to a lot of you. His name is John Ryan, and he is a researcher at MBARI. And I just want to point out the Monterey Bay National Marine Sanctuary Foundation does an award each year for excellence in research, education, environmental protection. And John received the inaugural award for research because of his work. And if you're ever over at the Monterey Bay Sanctuary Exploration Center in Santa Cruz, you'll notice an exhibit there that deals with sound in the ocean. And he was a very integral part of that. So the presentation by John Ryan is Tracking Whales by Listening. John Ryan is a biological oceanographer at MBARI, studying the ecology of plankton, fish, and mammals. I'm looking at him, he's behind the screen here. Brilliant person behind the screen. Primarily through integration of remote and in situ sensing technologies. Through science engineering collaborations, this research involves advancing methods of sampling and data analysis. You can find a representation of his work, as I mentioned, at the sound exhibit at Monterey Bay Sanctuary Exploration Center and other places. So I'd like to welcome John Ryan.
Thanks, Dan. And I'll follow in Natalie's footsteps and be mobile with the microphone. So yeah, I'm filling in for Will Astrike, who's a postdoc with us at the Monterey Bay Aquarium Research Institute. Will and I study similar topics, and we collaborate a lot. He's a good friend and colleague, so I'll do my best to stand in for him. And on short notice, I pulled up my ocean sciences meeting from New Orleans earlier this year. And today we'll talk about bluefin and humpback whales, but mostly blue whales, because we've had the best data resources for studying the movement ecology of blue whales and what that means for how we can better protect them. And this work involves many collaborators, including people who put tags on whales, Cascadia and Hopkins, so we can see the world from the perspective of the whale, the Naval Postgraduate School, the Sanctuary, Southall, Brandon Southall at SEA. So we use the term endangered species, and what does it mean? Well, it not only does it mean different things for different species, but it can mean different things for different populations of the same species. So here, this graph here shows the vertical lines are whale catch during the years of commercial whaling. And the blue line is the estimated total population size. And you can see that blue line drop precipitously with commercial whaling, reaching phenomenally low levels, really. But this is the southern hemisphere. And the population was brought down to less than 1% of its original size, and it really hasn't started to recover yet. Because if you reduce the population that low, it's very difficult for it to recover. The situation here in the North Pacific is somewhat better. The population was reduced to maybe a third of its original size, and there are indications that recovery has been happening. As far as the eye can see, how far is that? Well, from altitude, looking through a clear atmosphere, it's pretty far. 50 miles, easily. That's my wife Cindy and myself. And what does that mean at the surface of the ocean? And we should have a video play. Yeah. At the surface of the ocean, we can observe blue whales quite well, at least their surface behavior, like breathing. And, but when that whale dives, going down for foraging, it doesn't take long before it's just below the surface, and light is no longer really so useful for studying their behavior. And the relative importance of light and sound flips at the air-sea interface. Sound travels really well. In contrast to this short range of visibility, we can hear a blue whale if it's anywhere within about a 4,000 square mile area around our microphone. And the focal signal we're going to look at today is song. It's a particular type of acoustic behavior that baleen whales exhibit, rhythmic, structured sequences of sound. And that means different things for different species. So what you're looking at here is a spectrogram. Along the horizontal, you've got about 34 minutes of time. On the vertical, you've got frequency or pitch, higher pitch, lower pitch. And along the right there, you've got the approximate frequency ranges used by each of these animals, at least in this example. Humpback whales have the greatest range of frequency, and that's a logarithmic scale. So humpbacks in this case are between about 70 hertz, and we're going up to nearly 10 kilohertz here. All below 100 hertz, we've got blue and fin whales. And notice how they kind of separate the frequency range on and where they're putting out sound. Fin whales are in this narrow band between two harmonics of a blue whale call. Oh, yeah, musical interlude. So it's important that you hear these whales, I think. And so I was just behind the curtain here, hooking up the last bits here. So give me about 30 seconds, and you will soon hear a blue whale. That's one note of a blue whale song. And, you know, for a Wizard of Oz moment. Yeah, I mean, if you weighed 300,000 pounds, you could make that sound. But, you know, you really need a substantial speaker to represent that powerful low-frequency sound. If I put this out on the web, people would be kind of frustrated. They wouldn't hear it through their ordinary computer speakers. So that's one, that's a blue whale. Fin whale. Fin whales are almost like, they're very percussive. They put out just pulses. Each pulse is less than a second. And they might vary the pitch of the pulses a little bit, sometimes climb the scale a little bit, but you know, they're pretty much in the percussion section. Change of course. I think I'm going to tell the story of the blue whales first, and then we'll go back for another musical interlude. So next slide. Okay, so how do we listen? How do we listen in this region? We're going to fly into the Monterey Accelerated Research System, Mars Cable Observatory, connected to Moss Landing by a 52-kilometer, 32-mile cable. My office is right there. The cable extends across the northern continental shelf around, this is Soquel Canyon, south of Santa Cruz. And when we get to the edge of the continental shelf, you can tell the bathymetry drops off more steeply here onto the continental slope, a feature called Smooth Ridge, which is where the observatory sits, 900 meters. That cable coming in on the right is what connects us to shore, and the science ports are along both sides, 8 science ports. And as we zoom out from the observatory, you can see we're kind of in a natural geological amphitheater, open to the Pacific and the diversity of the species that produce sound. So it's a really great place to listen. Oh yeah, next. Next slide, and it's also a video. This is the ROV with the extension cable that plugs into the observatory. And there's a tripod, it's a little hard to see, but the hydrophone's right there. And let's get the next video will show you us plugging the hydrophone in. There's the hydrophone, just about as big as a soda can. And there's the remotely operated vehicle arm holding it in its tripod that sits on the seafloor. And maybe jump ahead about 10 seconds. Oh, there we go. Yeah, this is us plugging it in. And you know, sure, of course, you're under tremendous pressure and corrosive salt water. Just plug in an electronic device, it's going to work. And it does. But the connector required to make that work cost $25,000. Yeah, but it's, you know, it's really a phenomenal resource, unlimited power and communications, a live connection to the deep sea. Okay, next slide. Yeah, so this work was led by World Wildlife Fund and involved a number of universities, including UC Santa Cruz, Ari Friedlander there. And it shows you those pathways that these whales take in their annual migrations, from low latitude breeding habitat to higher latitude foraging habitat. Tremendous distances, and they need this habitat off this coast to tank up. They need to forage on really dense, blue whales in particular, forage on very dense aggregations of krill in order to build up those energy reserves needed for long distance migration, breeding, birthing, and rearing of young. Next slide. And this work shows some of the biologically important areas off California for the blue whale, and it's based largely on sighting data. It's a tremendous resource. And you can see the high densities of blue whale observations in Monterey Bay and north across the mouth of San Francisco Bay, Gulf of the Farallones. These are some of the important areas, but I'm going to focus on tracking whales by listening here in our region right here. And as we zoom in, of course, the sanctuary is such an important part of this ecosystem, really, because it's helping us to understand and manage and protect. And here in the middle of the sanctuary, this blue boundary is the main part of the sanctuary, and then Davidson Seamount, of course, very important region of biodiversity. But here the observatory is sitting largely in the center, right here as we saw. And on this map, there are two things I want to emphasize. This white circle shows the GPS location of a whale with a tag on its back. Before that whale came up to the surface, this is the Goldbogen Lab at Stanford, by the way, their work. And before that whale came to the surface and gave us a GPS location, it sang a song. The song was recorded on the tag on the animal, not just in the hydrophone, but in an accelerometer that measured the actual vibration of the whale's body. We matched that song up with the signal received here at the observatory, and this green beam shows the estimated bearing from the receiver to the whale. So this is, you know, answers the question, does it work? Which is, you got to start with that. So yes, we have confidence that it works, and then working with our colleagues at the Naval Postgraduate School, we need to know how far away can that whale be, and we can still hear it with sufficient intensity that we can reliably point to it. That's what this line here represents. It is blue whale could be anywhere in here, and we'd pick it up. We could point to it. And that's all theoretical modeling of sound propagation in the ocean. This map of sea surface temperature, cooler temperatures in blues, higher in yellows and reds, it shows the key process that we expected blue whales to be very attuned to, and that is coastal upwelling, where the winds out of the northwest move surface waters away from the coast, creating upwelling circulation, bringing deep water to the surface. And that deep water is cold and it's nutrient rich and it fertilizes the ecosystem. So the microscopic algae grow and everything else comes from that, including the forage species of the whales, krill, in the case of blue whales. And what we saw is that years ago in a paper published in 2019 is that krill form really dense swarms within these upwelling plumes. Blue whales have had millions of years to figure this out. So we predicted they would track these coastal upwelling plumes. Then lastly, we're concerned about their exposure to ship strike risk. So you can see in this heat map of vessel traffic, the shipping lanes just offshore of our recording site. And here's, the brave and bold souls who get out and with a small boat and place these suction cup attached tags on the backs of the whales. And so that is what allowed us to put confidence in our remote detection of the whales. That's Dave Cade on the front there. And one more. Yeah, so here what you're looking at is a number of years, 1, 2, 3, 4, 5, 6, 7, 8, 9 years of the seasonal cycle of blue whale song, quantified from that sound that kind of shook the room. And I'm going to focus in on just 1 year, the first year that we had on the observatory, not just an omnidirectional hydrophone, but an acoustic vector sensor, which measures not just the pressure signal like your eardrums are using now, but also the three-dimensional water velocity caused by the sound waves. So you can go beyond saying, I heard a blue whale, to saying, it's over there. And the great thing about passive acoustic monitoring is, it can operate 24/7, 365. You can just continuously observe, and there's great value in just the density of observation that gives you confidence in the patterns that you see, that you're able to describe. And so here's an example of how we do this. Here's the energy represented in color. You've got pitch on this scale and time on this scale. And each one of these swipes is one of those blue whale calls that you heard. And what we're doing is we're identifying the calls with some signal processing, and we're locking onto the maximum energy of that call and extracting the frequency that is at which the energy is at a maximum. And then if the energy is strong enough, we estimate the bearing to the animal. So you can see in this time period here, there are blue whales calling pretty steadily from south-southeast and from the north. And then there's one animal, the loudest one, relatively close to the hydrophone probably, moving, changing its bearing steadily relative to our receiver. So we can actually watch them move through the ecosystem just by listening. And here's that relationship I mentioned. And Kelly Benoit Bird is at MBARI, and she's led this study that examined the relationship between that wind-driven upwelling index, creating the cold plumes, and the aggregation index of both krill and anchovies. So there's this very strong, clear relationship that as upwelling gets stronger, there are more dense aggregations of animals that the whales are looking for. And here's what that looks like. If you were to use sound actively to drive along, leaving out a Moss Landing, drive along this transect offshore, you're right over Monterey Submarine Canyon here. And as you went offshore, of course, the bottom gets deeper. And all of this color represents the concentration of krill. And so there are two vertical sections along the canyon axis shown here. One when the bay was quite warm, relatively warm, and one when it was relatively cold. This is when upwelling is active. We expect the krill to be more dense. And this is when upwelling is relaxed. And using a remotely operated vehicle, Kelly identified that these indeed were krill, and compare the density of these patches in the yellows and reds to this, a much more diffuse distribution of krill. If you're a whale, you're going to get a lot more energy per unit effort if you find these during upwelling. So, okay. Now let's see what it would look like from the perspective of the whale. This is a krill swarm. This is actually at the depth of the continental shelf break, where the blue whales tend to forage. Extremely dense. I mean, I think I could swim around in that with my mouth open and get a few. Now, they wouldn't really be able to see this because there's not much, there's a near zero light down at this depth. So we're just using light from the ROV. And on the right, you've got a view of a blue whale on the left from the back of another blue whale. And watch as it opens its mouth and engulfs a mass of water that weighs more than its own body. And in about 2 minutes, it can squeeze all that water out through its baleen and retain the krill. Very efficient foraging strategy. And that's phenomenal footage from a tag from Jeremy Goldbogen's lab. Okay, so what about our hypothesis? Do blue whales track coastal upwelling plumes? Well, what you're looking at here are the two plumes we have in the Monterey Bay region. And these both are important contributors to the productivity of the whole region. And only this plume originating at Año Nuevo flows into the bay and into our listening domain, the region where we can hear the whales. In contrast, this plume flows outside of our hearing range, so we're going to focus on this one in the next part of this study. Nonetheless, if we add up all the whale calling, what bearing did it originate from? Received here. Here's a bearing to Point Año Nuevo, and you can see a peak around that. And here is the bearing to Point Sur, the Point Sur upwelling center, of which we hear only a small portion. And you see a narrower peak right there, probably because we're not hearing all of it. Nonetheless, overall, there's a clear relationship that they seem to favor this habitat. Oh yeah, and the edge environments are important. Okay, so they are. So now let's look at the winds change and the whales respond to the wind. What you're looking at here in this upper panel is the wind-driven upwelling signal. It's the upwelling index. And we have this major pulse of wind-driven upwelling, winds out of the northwest. Now you look at this middle panel. It's from this location in the mouth of the bay. It's a mooring. And if a cold, dense upwelling plume hits this mooring, we're going to see it. And it'll look like these lines of constant density rising to the surface. Cold, dense water is at the surface. The wind drove the circulation. Now this last panel is the percentage of call time from blue whales originating from this bearing range, the bay. So you can see winds, upwelling, whales move into the bay. Upwelling goes away, the upwelling plume dissipates, the whales move out of the bay. And then a second upwelling pulse, a series of pulses, causes upwelling plume at the mouth of the bay, episodically, and whales moving into the bay again. So they're very sensitive to what their ecosystem is doing on very short time scales. Now, what about when they're not in the bay? Well, during those relaxation periods, look at the red circles. Those represent the percent of call time from blue whales in this bearing range, which encompasses the shipping lanes. This is where they encounter the risk. So during these wind relaxation periods, there is elevated risk of ship strike. Okay, we're doing good. So protecting blue whales and blue skies, you know, one of the things we really hope for as scientists is that our research can help to protect the animals we love. And so I really appreciate this program, which is in partnership with the National Marine Sanctuaries Program, and the Sanctuaries Foundation is closely involved. But you know, this concern about ship strikes on whales in Monterey Bay National Marine Sanctuary has been here for a while. Our study just helped to add some perspective on when that risk might be heightened, for example. Nonetheless, the Sanctuary Advisory Council last year recommended that this sanctuary join this program. It was already active south of us in Santa Barbara Channel and north of us in the Gulf of the Farallones. And now it's active here in this sanctuary. And they recently reported highlights from the 2023 season. And you can see on the right the many shipping companies that have signed on and become involved. 33 global shipping companies participated, 81% cooperation, a tremendous amount of distance covered, reduced emissions from the vessels because when you slow them down, they emit less. Reduced risk of ship strikes, estimated significant, 58%, and reduced underwater noise. So there's a lot of good reasons to slow down. So what about fin whales? Well, you know, their body types are quite similar, you know, and their foraging modes, you could say, are similar, but the blue whale is larger than the fin whale. Nonetheless, they're here every year also. What you're looking at in this plot is the whale call index. In gold, you've got the fin whale, in black, the blue whale. And so, again, fin whales give us this tremendous opportunity to study the movement ecology of a species and how that maps onto our activities. Because if we want to protect them, we must understand where and how they live. And this is one tool for that. So let's take a look at fin whales relative to blue whales. How are they using habitat? Is it the same or not? So for the purposes of this, let's just draw a couple of bearings from our observatory straight south and to the northwest. And those two bearings roughly separate the deep water offshore habitat from what we might call the shelf slope habitat, the continental shelf and the continental slope. And we're going to look at both of these species in those two categories. So this plot, what it shows, based on just 1 year of data, is that fin whales in particular, strikingly, the percent of calling from deep offshore water is just persistent with fin whales. Most of the time their calling is 90% or more from offshore. They just persistently inhabit that deep offshore water. And likewise, you notice this is just the summation of all observations on the right here. For blue whales, notice they're mostly in shelf slope habitat. But what you really need to know is on the same day when they're both calling, are they in the same place? And that's what these circles represent. So for example, most of the matched of days where we're looking at calling from both species, fin whales are 90% or more from offshore, while blue whales are 90% or more in the shelf slope habitat. So Earth's two largest species seem to live largely apart. There are exceptions. We do see fin whales occasionally come into the bay. That does happen. But this is the type of information that would, for example, help us to be aware that fin whales are probably exposed to ship strike risk more persistently, simply because they live offshore in the offshore deep water habitat more persistently. On humpback whales. What about humpback whales? Well, what we're doing now, we're starting a project with a program called Hacking for Impact, and there's a group of students at UC Santa Cruz who are taking on this project. And the idea is, certainly humpback whales are also subjected to risk of ship strike, but one of the major problems they also face is entanglement in fishing line, fishing gear. And it can wrap around their flukes and cause really severe injury or even death. And so right now we use visual surveys to estimate the local abundance of humpback whales and where they're living. And that's a great resource. It's absolutely essential. But what if we could use an acoustic vector sensor to watch in real time the movements of the humpback whales? And so that's a project we're just now starting with Jared Santora, who works with NOAA and UC Santa Cruz, and this Hacking for Impact project with undergrads. Okay, next. So I am going to summarize before I go to the back to the musical interlude. Supporting the health of endangered species and protected species does require knowing where and how they live and how that intersects with what we're doing. And this particular integration of technologies is one approach that we're finding to be effective. Acoustic vector sensing, just by listening. We're just listening, not putting any sound into the water. Biologging, putting tags on the whales, and understanding what the ecosystem is doing. That has already shown us that blue whales are very responsive to wind-driven upwelling on short time scales. And that affects their foraging ecology and risk to ship strikes. And ongoing work now is revealing additional dimensions of this behavioral ecology for bluefin and humpback whales, and we are aiming toward informing protection. So I can kind of take questions while I cue up some music, whale music. Yes?
What is your understanding in terms of why whales are not able to avoid ships? Like, are they not hearing them? How does that?
Yeah, that's a great question. Why are the whales not avoiding the ships? I mean, these things can be 3 football fields long, massive things, easy to sense, you might think. Here, you can hear them. And Megan McKenna, who is at Stanford and Middlebury as well, she's living and working in this region. She led a really phenomenal study toward your question. They put tags on blue whales, and they observed the behavioral response of the whales to an oncoming ship. And what the whale did is just slowly submerge. The problem is there's a lot more ship way down below. And, you know, they didn't evolve with ships. I mean, stating the obvious, they didn't evolve to avoid that kind of threat. And so there was no observations of lateral evasive maneuvers. And, you know, that building on that type of study is where I think we need to go, more tags on more whales, because who knows, maybe some do a better job than others. But that's the other thing, though, you know. Well, I guess I'll stop there. It's an important question, though. Thank you.
Why can't they make a noise that the whales wants to hear?
Yeah, that's a good suggestion, that you could send out a warning noise ahead of your ship, and if the whales could interpret that. Yeah, that you're hitting on both the answers. You know, whether or not the whales could interpret that as move out of the way, or how much noise would we be putting into the ocean ourselves in the process. So, good question and good answers, both from you.
Thanks for the talk, very good. I was curious, how much issue do you have with noise pollution from ships or other things that you're picking up with your mic?
Yeah, noise pollution is really a Yeah, that works. That works. So, and about probably 15 years ago, NOAA, long has NOAA, Protected Species and Habitats, and a new emphasis emerged in that, and that is protection of acoustic habitat. So they wrote an ocean noise strategy roadmap to help us begin to work together toward understanding and solving that problem. But certainly shipping is a major source of low-frequency noise, and for a while it was doubling every decade. That tends to shrink the communication range of the animals. They can't communicate with each other as well. There are also problems of impulsive noises. 350. Oh, oh, I got plenty of time. Good. Yeah, there's like. There was a phenomenal, unexpected experiment in the Northwest Atlantic you may have heard about, and that was when 9/11 occurred. Shipping was shut down off the northeast seaboard, and that meant noise levels in the ocean dropped significantly. And people happen to be monitoring stress hormone levels in North Atlantic right whales during that time. And that period when the ocean went quieter was the period when their stress hormone levels were the lowest. So it's only one study, and we need to do more, but that suggests that the rest of the time, when we're going about business as usual and pumping a lot of noise into the ocean, it does stress them. As you can imagine, it would us if we're trying to have a conversation next to a jackhammer, you know. But let me stay with your question, because I think there's more to it. Was there, yeah.
Like the analysis piece, how does it interfere with your interpretation of what's going on in the ocean?
Oh, how does noise interfere with my ability to study life? Well, you know, I have good examples where you'll see a beautiful whale song, and then it'll just get washed over by shipping noise, and so it just limits the amount of time when I can pull out signals that are from a biological source and study a species, pretty much. And but you know, I guess it's worth saying in relation to your question that when we go to the next question, which is, you know, from where I'm listening, if I see a beautiful whale song get just washed out by shipping noise, what the whale experiences depends on where it is in relation to the ship, because it may experience a very different noise level than our receiver. Yes.
Are there plans that you're aware of to place more of these Mars units along the West Coast?
Yeah, the cable observatories. There are others. Canada has quite a number. There's a possibility that a collaboration between science and industry could open up more cables as we develop offshore wind energy. And further, there are other phenomenal sensing systems that can tap into cables and hear whales. And my favorite recent example is, it's called distributed acoustic sensing. It's sensing sound using light. They send light down optical fibers and cables, and measuring the strain in the optical fiber caused by a sound wave, you can not only get a clear signal from a biological source, especially the low frequency whale calls, but if you can create virtual hydrophones all along the optical fiber and localize the animal. Where'd that sound come from? And so this is called distributed acoustic sensing, and they use interrogators that plug into the end of a cable. Yeah. Yes.
Why don't you guys use 2 mics to localize stuff?
Yeah, that's right. That's a long-standing method. You put out an array, and if you know exactly what time it is on every node in the array, and the animal calls from within your array, you can triangulate and define the position. And in the Northeast Atlantic, where the North Atlantic right whale, critically endangered, where it's so important to avoid ship strikes, they've done things like put out hydrophones on gliders, not even moorings, mobile platforms that are synchronized well enough to localize the animal and automatically send through satellite a message that alerts ships in the region. And now here, why aren't we using an array, or why aren't we using more than one? Well, we did put out 2 acoustic vector sensors, we being the Naval Postgraduate School and MBARI in a collaboration. And we collected about a year of data, and we're beginning to look at that. Can we use the signal received at 2 nodes to not only get a clearer signal overall, but also get 2 bearings, find their intersection for a range? We're trying that, but it's what the person who's leading that, Paul Leary at the Naval Postgraduate School, told me is, it is challenging, because if you have a little bit of error in the bearing from 2 nodes, your uncertainty in the range gets significant. Is that answering your question? Okay. Yeah.
The previous speaker mentioned that with climate shift and climate change, there may potentially be more whales coming into the Monterey Bay area. You mentioned that winds coming from the northwest
Yeah, that's a great question too, because climate change does affect these wind patterns, sea level pressure patterns, and winds. The two upwelling plumes I emphasized, one at Año Nuevo, one at Point Sur, that's part of a much larger ecosystem that has the same fundamental physics. Northwesterly winds drive coastal upwelling. So the California current ecosystem extends from, it extends over tens of thousands of kilometers. Yeah, it's a huge ecosystem, and so we're, in a way, what we are is representative. And there's been a long-standing question about whether upwelling will actually intensify in the California current ecosystem as a result of climate change, which in a sense would intensify not only productivity through increased upwelling of nutrients, but that cold, dense water would mitigate sea level rise, because the dense water takes up less volume and sea level is actually lower. Yes?
I listen to the hydrophone most evenings and mornings, and I can confirm wells quite a few times. Is there anything that's able to be done with that data? I know they're much more cryptic than like humpbacks and stuff like that. Is there anything you're able to do with that, the songs from them?
I wish Will Astrike was here, because he has a paper and review on sperm whales. So first of all, thank you for listening to the live stream. We have a live stream. You can listen to the Deep Ocean anytime online on our website. And this time of year, it's not particularly exciting. Fall is awesome with whale song. But sperm whales, you know, if you ask a whale watch boat naturalist, how often do you see sperm whales? The answers I got were typically rarely. One answer I got was about once every 5 years. So Will led a study where we asked the question, how often do we hear them? And the answer is very different. In the last 8 years of continuous recording, we hear them about half of all the days we've been listening. So if you were to ask the question, how important are sperm whales to the biodiversity of this sanctuary? You know, the limited visual observations would give you a low number, and the audio recordings give you a much higher number. Yeah.
So it looks like the slide that had like the blue whales were down here and then some fin whales. It looks like you're scanning a large frequency. Is there ever a time where you would maybe scan a smaller frequency looking for something very specific? Is there a use for that? Or is it just really important to scan the whole thing?
Yeah, if your goal was biodiversity monitoring, you would definitely want that very high sample rate that allows you to hear sounds well outside of our range of hearing, but very important use by dolphins, porpoises for echolocation. If you wanted to only study blue and fin whales, you would do quite well recording at a very low sample rate and just focusing in on that. But the benefit of being on a cable observatory is that we're not bandwidth limited. We can just stream very high sample rate data to shore, store it, and we can analyze that low frequency and on up. In fact, that call index I described is based on looking at a really narrow frequency band, because blue whales put out stereotypical calls that always land in the same narrow frequency band. Specifically, we target the third harmonic of their call because it has the most energy, between 40 and 45 hertz. So 5 hertz out of 100,000. Yeah. Yes.
One more question, it's more of a girl question. Of those sperm whales that are heard so frequently, are they mostly offshore? Versus in the slope, shallower?
Yeah, mostly offshore, that's it, you know, because whale watch boats naturally are going to go to the nearest place to find whales, although sometimes they'll do an all-day trip that allows people to get farther offshore. And my favorite story is actually from Kate at Blue Ocean Whale Watch. She wrote me one day and she said, hey, you know, just wanted to let you know I was listening to your live stream this morning and I heard what sounded like 3 sperm whales. And then in parentheses she said, like 3 people in tap dance shoes walking out of Stride. And so I said, well, that inspired her. That day, they went for it. They went far offshore looking for these sperm whales. And on the way back in, I think it was, they found 3 sperm whales. Yeah. So they are deep water squid foragers, so makes sense.
All right, thank you, John, so much.
Right.
Incredible presentation. And thank you for all you do, and in appreciation for your presentation today, a little steam of our gratitude.
Thank you.
Thank you,
Dan.
sir.
All right.